Okay, good afternoon, everyone. Welcome to the ECE research seminar in November. This time, our speaker is Dr. Ali Gurbuz. Dr. Gurbuz received his PhD degree from Georgia Tech in 2008. Then from 2009 to 2016, he was an assistant professor, then associate professor at TOBB University in Turkey. He joined our department in 2018. His research interests including machine learning, signal processing, radar signal and array processing, and so on. With this very brief introduction, I give the floor to Dr. Gurbuz.
Thank you very much, Jenny, for the introduction. So today I will talk about compressive sensing and machine learning and how we can really relate these two different concepts, sensing and machine learning. And I would like to start with the compressed sensing. This is kind of the first application and the most well-known application for compressed sensing is a single pixel camera. Basically, you have, instead of a billion photo detectors or pixels, you are taking single measurements for an image, and using these different type of measurements, you can really reconstruct the signal back. So this is kind of a good application for compressed sensing. And let me show you how really this is related to the general framework of signal acquisition and reconstruction. Generally, we have an analog work, right? We have signals that we either, for example, images, sounds, it could be, for example, ourselves, a brain image that might be, or a tissue image that an MRI machine might be taking, or a radar image is trying to understand a word, for example, right? And what we do to understand this is we sample, right? And this sampling can be in time, in space, and the analog to digital converters who does these data acquisition and sampling for us, they are fixed, right? They do kind of sampling in terms of whatever the Nyquist rates are telling them, and depending on the application, bandwidth of the signal, and it's creating too much data. We are taking that in digital world, and the signal processing part of this is really trying to understand this data in another domain and kind of either do an inference, classification, estimation type of applications, or reconstruction of signal and to further process it, right? So, but the signals are much simpler than that the raw data we collect. Because, I mean, for example, you see an image over here, we can compress this image and represent the same type of information with much less number of coefficients. Okay, basically the information part of the signal is much less compared to the total number of measurements for the signal. So this fundamental concept is known as the transform domain processing in signal processing area. And what we are really doing is, instead of this raw data measurements, which perhaps if you think about this, 1,000 by 1,000 image, perhaps a 1 million image pixels or measurements, we transform this image into a domain where we can have less number of coefficients, or the signal is sparsely represented. For example, if it could be a DCT basis, discrete cosine transform basis, where your JPEG compression is, right? Or it could be any other dictionary that you might be suitable for the signal you are looking for. So basically, what the general data acquisition and reconstruction or compression framework is, taking these measurements as the Nyquist rates are suggesting, and collecting the n number of measurements, but compressing it and kind of storing only k coefficients, kind of the sparsity level of the image, or the information level of the image is K, where this number of measurements are generally much higher than that. When you are trying to do anything on the signal, basically you work with these K coefficients, reconstruct back the signal, and then do some inference or processing, classification or something like that on the image itself, right? So the main thing we are looking for this is, I mean, why are we going and acquiring all the measurements, this n number of measurements, only to discard but keep only K pieces of the data? And the compressed sensing just trying to acquire this information part of the signal directly while in the data acquisition process. It's not just kind of taking a fixed way of let's say uniformly sampling data acquisition approach, but it's asking the question of, can we really directly measure this with kind of less number of measurements, and really perhaps instead of an analog to digital conversion, perhaps our approach might be an analog to information conversion. Okay, so in this one, you can think about what kind of measurements we are taking. For example, you might think about your measurements as the projections of your signal into some measurement vectors. For example, in standard sampling, basically you have a signal and your measurement vector is just a vector like this one. You might just think about the vectorized version of these so that you might define these projections. But this is the standard sampling, right? But in, for example, MRI, you are taking measurements in frequency domain. In terms of the spatial domain, you might think about correlations with these sinusoids. Or in topography, for example, we are taking measurements as line integrals at different angles. So the question is, how should we measure a signal? Right? What should be the projections that we use over here so that the number of measurements that we can take is minimized and we can get an adaptive performance from a fixed set of measurements? This is what the compressed sensing is looking for. Okay, and what the result is, if the signal is sparse, where most of the natural signals are, and it says it is sparse in a known basis, such as the discrete cosine transform or Fourier transform or wavelets or a dictionary that you perhaps came up with, then the signal can be reconstructed using less number of linear measurements. So basically what we are saying is this: B is your measurements. We have a system A where the number of measurements is much less than number of the unknowns n, the signal dimension. And in that case, what we know is we have an infinitely many solutions to this linear system, right? But we are enforcing a sparsity on the solution. And that enforcement is done using an optimization problem where we are minimizing, for example, the L1 norm of the x constraint to y equals phi x. This one telling us that out of all the solutions that satisfy your measurements, you are looking for the one that is the most sparse. Okay, and we have theoretical results that shows the number of measurements for perfect recovery is in the order of sparsity or the information level of the signal, and which is much less than the number of the dimension of the signal. So this is just an example. I mean, for example, we have a sparse signal in frequency domain, let's say 10 non-zero frequency components. In time domain, it is not sparse, but in frequency domain, it is sparse. And in time domain, normally you have, I mean, the dimension of the signal for this random example is 512. You might just take randomly 50 samples of this. And when you do the reconstruction, you see that we can perfectly reconstruct using this sparsity approach and the usual way of L2 norm minimization is just giving incorrect results on these, or not good, at least. Okay. And this CS has shown to be successful in various applications, most well known in terms of computational imaging, MR or radar type of imaging, hyperspectral communications, but anywhere actually where taking measurement is expensive or costly, and this cost can be defined in terms of the time that the measurement takes. For example, in MRI machine, instead of waiting 30 minutes, you might just wait 3 minutes, just take the 1/10 of the measurements, and using this, similar quality images can be reconstructed. So time could be a cost. Space could be a cost, where if you have number of sensors and you are creating an array, then you might not really need to have that many number of sensor points or arrays or space, so that you might take much less number of measurements. And energy, in terms of communication energy or the energy for a data acquisition, such as in the seismic imaging cases. So for all of these cases, compressed sensing is really a good solution. And it's exploiting the data acquisition. It's universal in that sense that it's using the same random projections or hardware for any compressible signal class. So each measurement is equally important and unimportant, so it's democratic. Since we are doing the elections right now, I guess a democratic this approach or technique is really a good thing. So if we, for example, lose a high coefficient in your transform domain, you might be losing most of your energy, while if you lose one of your compressed measurements, you might just take another one in terms of it's another random projection there. Okay. We are sampling less, but the reconstruction is much more computational, so more compressed sensing on this one. So this, I hope it's a very brief introduction for compressed sensing, but I hope it gives us some idea of what it does. It's mostly related to the data acquisition part of this signal acquisition and processing chain. While the machine learning is, we have labeled inputs, at least for the supervised case, and we are trying to perhaps understand from data that classification or regression type of problems, right? We need data, labeled data, and we are trying to understand those. So let me try to show you how these really come into the same playbook. So basically, when we look into the sensing and processing chain, the classical approach is, as we talked about here, for example, we have a signal that we want to acquire or sense. We have different type of sensors or data acquisition systems, either use this classical approach in terms of Nyquist sensing or compressed sensing in terms of if the signals are sparse. So we have different choices over here. Depending on those choices, we have measurements, and each of these different sensor types might be using any of these data acquisition approaches. So from these measurements, basically, you might do a reconstruction, and on these reconstructed images, using many of those, we are trying to do inference, and machine learning generally come into place at this point in this processing chain, taking many of these different input cases and trying to map these to the actionable information, such as the classification class or a regression variable or so. So kind of in this block or in this chain, the compressed sensing is at this data acquisition part, while the machine learning is really at the end, at the inference part over here. But when we look into this, one problem is that each block is optimized separately. So when the Nyquist data acquisition or compressed sensing is looking into this problem, it's just at least for the Nyquist, it's just looking what's the bandwidth of this signal, so that if you want to reconstruct, I can reconstruct without really losing information, right? That's what it is really interested, and it's just interested between its own input and output. It is not really looking into any information from the inference approaches. If for example, we are going to do classification on this image, or if you are going to, let's say, estimate a parameter about this signal, it doesn't really change its way of acquiring the signal depending on what type of task that output will be used. So in that sense, each block is optimized separately. When we are doing reconstruction, we are just taking the measurements and trying to minimize the, let's say, mean square error for this block input-output relation only. So this approach for each block being separate is really a problem. And for this case, I mean, when we look into those reconstructions, exact inverses might not be known. We have sensor modalities, non-idealities, noise. So each part has its own different problems, and really working or optimizing itself independently or separately from other blocks. So our question or goal is really, can we jointly optimize this different blocks? And instead of really using fixed approaches, can we use machine learning based structures for both the data acquisition, reconstruction, or classification? So kind of, can we bring this classical approach of sensing and processing chain into a learning based sensing framework? Okay, that's kind of the goal. In that sense, if we could do that, then a machine learning type of structure will be looking in terms of at least learning the optimal measurements. For example, what should be the camera should be acquiring for a given task, or what should be the measurements of an MRI machine, or how the radar should take the next measurement given its current state and system is this. And can we optimize these or learn these with the tasks that this system is doing for the reconstruction or for the inversion or inference type of things? And hopefully use the actionable information as, for example, the output of a regression variable or the class that it estimates for a feedback for the next measurement. So adaptive type of measurements for this. Okay. So in terms of learning the measurements, basically compressed sensing suggests random linear measurement structures. Okay, and so it says that you can just do random linear projections of your signal, and those projections can be used to reconstruct the signal if the signal is sparse. So, but it is not really depending on, it's not task oriented, it's not adaptive, basically suggesting a fixed set of measurements, random linear measurements to do this. But there are ways that we can also optimize that random measurement structure. So create an optimal measurement matrix. Let's say this is what your projections are. We can create that. The relation between the sparsity information, which is, the informative part of the signal, and a mutual coherence of your sensing system A, which is combining the measurement matrix and your sparsity basis, is critical. So it is really related to that sensing structure. So if we have lower mutual coherence sensing systems, then using the same number of measurements, we can reconstruct higher sparsity information. So more information from the signal, let me say. So we can design these measurement matrices, and in compressed sensing approaches, it's shown that for given known bases. So if you know that your signal is, for example, sparse in Fourier domain, or it's sparse in, let's say, discrete cosine transform, if those bases are known, then you can really design measurement matrices that will be optimal for minimizing an average mutual coherence. Not the actual mutual coherence, but the average mutual coherence. Okay, so there is a way to optimally design these measurements in compressed sensing, but it requires this knowledge of sparsity bases and also somewhat not directly related to the reconstruction performance. So in terms of looking into this problem, we have sensor outputs, measurements, okay? And these measurements are living in, let's say, m-dimensional space. We have m measurements for sensing a signal type, okay? So these points might be different type of measurements in that m-dimensional space. And each of these measurements really corresponds to a different image in the reconstructed signal domain or image domain. And these really live on manifolds. So the sensor domain manifold and image domain manifold. What compressed sensing or the sparsity-based reconstruction approaches are doing is taking these measurements and kind of solving inverse problems to map these measurements to from sensor domain to image domain. So the question we are trying to solve over here is, can we do this image reconstruction or the mapping between the sensor domain or image domain, that function, as a data-driven supervised learning problem? Okay, so since the machine learning algorithms or structures are really good function approximators, can we really find this inverse function G between these two domains using machine learning? So that's kind of the question over here. And we want to do this together with the data acquisition so that we also learn the measurements and the reconstruction scheme together. So when we look into compressed sensing way of approaching this data acquisition, basically what it says is, sorry, your measurements are just linear projections of your input signal X, such as this Y equals phi X, okay? So it's modeling the measurements this way. So what we did was, we can model this same structure using neural networks, right? You might have the same input, and each row of this measurement will be kind of combining these weights, where the projection and this measurement matrix elements are the weights of your neural network right now. And compressed sensing suggests a linear projection structure, so that we might have linear activations in our neural network structure, so that we can model this data acquisition scheme using a layer of our machine learning network. Okay, so when we do that, we kind of modeled the reconstruction approach in also compressed sensing. So we have this image. So as you see, this is our input image. So this initial part over here is modeling our measurement structure. That it's kind of modeling this Y equals phi X. So the reconstruction algorithms generally start with creating an initial point for reconstruction. So something like a pseudo inverse or an adjoint operation, so that it has a proxy image. And then from this proxy image, either do iterative type of approaches or kind of solve iterative optimization problems inside that too, to get to the final image. So we kind of imitated that structure with machine learning over here. So this second layer over here is kind of trying to create a near proxy image structure, look like the adjoint operator. But now these things are learnable parameters. So if we learn, for example, this part, we will be learning the parameters of your measurement matrix. For the reconstruction network, we did a multi-stage convolutional neural network structure. And what we did as an additional thing is we forced the neural network structure to generate closer images after each stage to the original image. So kind of we take these mean square errors from each stage output and combine, kind of have a total weighted mean square error so that the final image has a better reconstruction. You might just say that you might just look into the reconstruction error between the original image label and your reconstructed images using that. But this multi-stage approach, forcing the kind of inner layers outputs to create as much as possible closer image reconstructions, seem to generate much better performance. That's what we saw in our structure. So what this one is really doing is it's learning the measurement matrix jointly with the reconstruction. So it's for reconstruction task, it will be learning this phi. And it doesn't require any sparsity basis to be given this. It is learning the best optimal sparsity basis, perhaps. It's from the given data itself. So you don't really need to provide any sparsity. Also, after we learn this, the expectation is reconstruction will be really fast, because one problem with the reconstruction is it's computationally very complex, because we are solving optimization problems to achieve the reconstructed signals. Right now, when we train this machine learning structure, when it is learned for the test case, we are just running it and the result is direct. It's very fast. So what we did was we tested this on CFAR10 dataset, which is kind of a small size image dataset. This is, you are seeing kind of, there are 60,000 images and we use 50,000 of them for training and 10,000 for the testing. And this is kind of our loss function that we use. And these are reconstructions from the images are 32 by 32. Kind of we are using 25% of the all possible measurements in these cases. So instead of having full measurements will be 1024, we are just using 256 measurements, 25% of them, and trying to reconstruct the original image. And the upshot of all of these things are basically the learned and our approach for the machine learning based reconstruction give much better PSNR values. The reconstruction errors are much less compared to the direct application of the classical approach of reconstruction, or initial versions of this machine learning based reconstruction approaches. And if we use the learned measurement matrices that are learned from our approach in L1 reconstruction, those also perform much better than the designed approaches, because designed approaches are specific to a dictionary, while our approach learns measurements for the given data set. So we are really doing much better, even if we just remove the reconstruction part and take only the measurement matrix and use it for the already existing reconstruction techniques. Those measurements perform much better. Okay, so you might just say you might be just training into a small group of objects. That's why it's only learning those reconstruction of those objects. It's not really. For example, CFAR is a small data set, but it has 10 different objects. What we did over here is trained the structure with, for example, nine objects and tested it with a totally different structure. And in that case, we also saw similar performances. So even though it's data dependent, it can reconstruct other type of objects or images that it doesn't train on. So another additional structure development on this one was the generative adversarial neural network structures, GAN structures. So what we did was take the image. This generator network is our proposed deep neural network structure that I showed you in earlier slides. And we kind of put this into this GAN framework, where this is looking into a different loss, where this generator tries to make this image, which we might say a fake image, because we are really reconstructed. It's a reconstructed image, but we are giving the original images, and this discriminator network is trying to force this generator network to create images so that it really looks like the original image. So this GAN structure also helps a little bit more, and the approach is not really only applicable to those type of small images. So I show over here different type of reconstruction on the large LANA image, with again only 25% of the possible measurements. We show that this is our proposed approach, and this is the GAN structures additional approach, which gives some type of an additional 1 dB PSNR on the reconstructions. So we can really reconstruct these much better than the current state-of-the-art approaches for this. So these are giving some type of reconstruction performances, so showing that the learning-based reconstruction is doing much better in terms of PSNR as a function of measurements. Also, it kind of has the same structure as the compressive sensing. When you increase the number of measurements, you can get higher sparsity levels of signals to be reconstructed. So as you see, when you have lower sparsity values with the same number of measurements, you can have better PSNRs. So it is trying to capture the underlying sparsity of the signal somehow, but it is not really dependent on a fixed dictionary. So as we have more training samples, it looks like we are doing a little bit better. So instead of 50,000 training, if we, for example, train it with 10,000 and test it, or if we include data, let's say 20,000, 30,000, we see that we are doing better if we have more training data on the sense. And as we expected, the computational time is much, much better than the compared L1 reconstruction, the optimization time that optimization requires. So significantly lower computational complexity for reconstruction. So in final several slides, I would like to tell you, okay, we are really doing this sensing and reconstruction perhaps together right now with a machine learning structure, but this inference, which was the most of the machine learning that's applied right now, is over here. It's just the general classification estimation problem in any application you can think of right now. But the final goal generally is not to reconstruct. In most of the applications, the final goal is to achieve this actionable information. Is this a cat or dog, right? So you need to find the classification output from the measurements from these raw measurements that you sense. So your final goal is either a detection, estimation, classification. So basically the final goal is an inference. And the general or the typical application for this is two-stage. You reconstruct the signal first from these raw measurements and do inference on these reconstructed images. Okay, this is computationally complex first because it requires this reconstruction part. Second, the measurements or the reconstruction approach is not really task cognizant. For example, an MRI machine looking for let's say, brain tumor, it's taking the same type of measurements, I don't know, looking for, let's say, some type of other illness in the body. So depending on what type of inference that's done over here, can we really optimize this thing all over jointly so that the measurements is also task cognizant. So in this one, this structure is known actually as compressed learning, and the general approaches is just using fixed, for example, sensing measurement matrices, and using a proxy, again, fixed proxy image. This phi is fixed. So creating a proxy image and running classification on this one. And the most kind of updated ones are just, instead of using a fixed measurement matrices, just learning a measurement matrix over here. So instead of that, we propose this type of a solution for all of the joint compressed learning framework, where you can learn the sensing part, as well as we are proposing this kind of reconstruction network, machine learning based reconstruction networks, and then apply this classification approach. So an end-to-end solution, but additionally, we also included kind of a novel loss function over here. Instead of just looking, for example, if you are doing a classification, the loss function you are interested in is something like a cross entropy. Okay, so you would like to minimize that type of a loss. But over here, I would like to do a kind of weighted loss function, because I want this reconstruction output to be close to the image, as well as I also want this classification on or inference networks output cross entropy, or if it is a regression, perhaps the regression cost, to be minimized also. So we have a total loss that takes care of both of them. And the learning is kind of minimizing, learning all the parameters over here, minimizing this total loss. As you see, this total loss is a combination of reconstruction plus this cross entropy term with a weighted structure. When we look into this, we see that this combination really gives a better approach to this, because when this lambda variable, that weight variable between reconstruction and classification errors, when it is 0, basically we have the highest PSNR, because we are not really interested in the classification errors, but only looking into the reconstruction error over there. But the accuracy level is really much less. The best accuracy is kind of the final result is achieved. Perhaps the system is not really reconstructing something really perfectly, but learning the best type of representation of that signal for that classification problem to have the highest accuracy. If you don't reconstruct the signal, and if you just do a kind of pseudo inverse input, then the accuracy is really bad, because the input signal is not enough informative for the classification network to do its job. So we see that this type of a weighted loss approach gives us the best performance, and also it's learning the measurements specific to this task. So we looked into as a function of SNR for these type of things, and we see that our approach even works better than doing the reconstruction first, and then applying the classification on that reconstructed images, the separate images, and much better than the existing compressed learning approaches. So deep joint compressed learning is kind of giving you a task cognizant measurements for different tasks, for reconstruction or classification type of tasks, and it can be learned or utilized, or basically this basically provides you a framework. It is not really defining the specific reconstruction networks or classification networks that you can use inside it, but it is defining the framework. So it's flexible which approaches you can use inside that. And when we have joint learning, we see that it's much better than the separately doing this operations. So as a conclusion, what we saw in our research, at least until now, and I should mention that this is most of these compressed learning results, which generated a kind of 2 papers right now, is my PhD student Rafi's outputs. I would definitely recognize him as well over here. So what we showed was this current sensing and processing steps include these independent approaches, blocks where each block is optimized separately, and they are fixed and not task oriented. And compressed sensing basically revised the data acquisition part, but still fixed and just looking for the reconstruction only. And we show that the machine learning framework can be combined with the compressed sensing type of an approach, where we can learn the optimal measurements as well as the signal reconstruction and inference. So this kind of opens a way for, I think, next generation task cognizant sensing systems, where the sensors can use different set of measurement types for what type of operations those measurements will be used. Okay. So I would like to conclude at this point. I think I finished at 1 hour. So if you have any questions, I would be happy to answer. I would like to thank you for coming in and listening to me instead of just looking, I guess, for the election results. Thanks a lot.
Thank you, Ali. If there's any question, you can type in the chat board.
Ali, can I make a short questions?
Sure, go ahead.
I partially discussed this before. I'm handling the real-time systems. So in the real-time systems, there's a voltage, currents, and power signals. The problem is that we don't have enough communication bandwidth. Another problem is that we cannot do the compressions either. So we have to, if we want to send this data outside this, then we have to do very sparse samplings. Can your algorithm also can be applied in such data signals?
Yeah, it could be. The point that we should be making sure is the data you are collecting should be sparsely represented in a domain. If that is possible, we can take it and we can compress it this way. But the approach, the compressive sensing approach, really is not an approach for compression, for not the best compression. If you are doing a compression, you can take the full data and really compress it in what domain you would like to compress, and just send that data, for example, from your communication link. Compressed sensing is much better. Instead of taking all of those measurements at the first place, it's just taking a little bit higher than the compressed kind of, because compressed is you can just take K measurements after you do, for example, compression. This one is taking a little bit more because it doesn't know where these coefficients are. But it doesn't really need to take the whole set of measurements in the first place. So it's mostly suggesting actually way of changing the data acquisition part. So it can help, but if you are if you are already taking the measurements and just looking for a way to best compress it, this is not the way. You should look for compression algorithms and best kind of dictionaries that you can use to compress your data. and you might have dictionary learning type of questions. If you have good amount of data, you might use, for example, the best dictionary that really sparsely compresses your existing data set. You might look into something like that.
Okay, thank you, and thank you for the great presentations.
Thank you for listening, Joy.
Okay, I did not see any question typed in the chat board. Hi, Ali, I have a question. When you evaluate the reconstruction, the signal to noise ratio is the only one you used?
For different performance, you are saying for the reconstruction?
Yeah, I'm just wondering how you gauge that reconstruction performance.
For the reconstruction, we use the peak signal to noise ratios, PSNRs.
Yeah,
for
that's the
our
only one you used. That's
Yeah.
the only one you used.
I think the papers, yeah, that was kind of the metric we used. I think the only one is that. And
Okay.
the loss function we used is kind of a similar kind of structure, which is related to the mean square error.
Okay. The reason I ask is because when I check that reconstructed images, I think they actually are very close. So I'm not sure, like when you result had some increase, 1 dB, 2 dB, but there any kind of inference in real application, in some kind of more specific application?
I mean, in terms of, when we are doing the, let's say, reconstruction, our approach is reconstruct only, right? So we are not really interested in terms of inference after that. But for this compressed learning framework, what we are doing is jointly reconstruct and do the classification together. So over here, we are showing, for example, the testing accuracy. Over, I guess we used, it should be CFAR10 data set only for that too. So the output is classification for that 10 different classes for different SNRs, the input SNRs over here. And what we are showing is it's doing a little bit better. We have the actual table values of these two, but it's doing better than giving the reconstructed images and then doing classification on those. So
okay, I see.
It's doing better in terms of classification too.
Okay, I see. Okay. So like you use the reconstructed image you generated, then classification accuracy is also
yes. This separate is that one. So we are kind of reconstructed the images using the same number of measurements. So all of these ones are kind of doing a raw data. So from 256 measurements, for example, raw measurements directly to classification. Our approach is not really, since it's machine learning approach, the final output is just the classification from these 256 measurements. But this one is reconstructing a kind of image in the middle and training on those images for that classification problem, and then achieving this type of a result at different SNR levels. These two other things are the other existing compressed learning structures, again, from the raw data from those 256 measurements directly to classification. But since their reconstruction part is not really good, I think we think at least that they are lacking that. Their results are much worse compared to the separate reconstruction part. Since we are doing it jointly, I guess that's why we are doing much better in terms of classification also.
Okay, thank you. Okay, there's a question from chat, Whitney. Sorry if this was answered. Can it learn from the sensing layer and not reconstruct, but classify on the sensing?
Yes, it is actually directly doing that because as you see, this full thing is our machine learning structure right now. Although we have kind of a layer and the output of that layer is some type of a reconstructed image, this is not the final output. The final output of our machine learning structure is this predicted label. So what it is taking is, after we learn this, we are learning the sensing part, right? These are the measurements that you can be using for your compressed sensing structure. So after you learn this, you can take this out. You can take measurements with this learned measurement matrix for this task, because you learned these measurements specifically for this task right now, and input that measurements to your network and just achieve your predicted label. So it is a direct inference from the raw data, from the sensing part, to the classifier, without really requiring to reconstruct a middle image.
Okay, great. There's let me see. There's actually the comment, not question, comment from Chase Robinson. I have no questions, but this was a very interesting presentation. You communicate the ideas in a way that an ECE newcomer like me could follow without losing the complexity of the topic. Thanks for sharing. Yeah, I would like to echo his comment. Thank you, Ali.
Thanks, Chase, for listening and coming in. If you are interested, please, contact me. I will be happy to share more if you have questions.
Okay. Is there any other questions from the student, professors? If your question is long, you don't want to type, just go ahead to ask, Ali.
Yeah, definitely. Also, I should remind you, this is my email or website. So if you don't have questions right now, but think about something else later, just write to me.
Okay. Okay, if there's no more question, I think we can conclude this seminar.
I would like